If you look at what kind of aging standards we have for rubber, we have the general ISO 188. We have also one for doing aging test in liquids, ISO 1817. But then we have the relaxation. Most common one is ISO 3384. It's relaxation in compression. And we have another one, ISO 6914, for testing in tension. The test in compression is mainly the one used because most of the materials and products you are testing are related in some way to sealing function. And then it's quite natural to do it in compression, where also two of the sides are protected and only a smaller volume of the sample are, say, in air. In tension instead, there you have a strip, which in fact should be only 1 millimeter thick, with the idea to have full exposure for the oxygen in the atmosphere. And that standard is also called that it's an pure aging test. So there is difference in the results between these two tests, mainly depending on the exposure for oxygen. What instruments are we using for aging? We use cell ovens, we use cabinet ovens, and we can use containers, testing liquids. And for relaxation, we have relaxation rigs, which can be equipped for testing in compression or testing in tension. In our main standard, ISO 3384 Part 1, it's called nowadays because we added a Part 2 some years ago. We have, in fact, two ways of doing it. Method A is a measurement at test temperature. It means that we measure the counter force at the test temperature. And we do all the measurement at test temperature. In method B, the measurement of the force is done at laboratory room temperature, normally 23 Celsius. And then the test jig is put into an oven for aging and taken out, cooled down, measured again at lab temperature. And this was the way of doing it originally before we had more of these continuous stress relaxation instruments. The method A and B gives different results. B, we also have the effect of the rubber shrinkage and expansion when we change temperature. The C here is not really a separate method. It's a way of measuring in liquids. And that is normally done on rings. So we have the liquid both inside the ring and outside the ring. Then all these measurements can be done discontinuous or continuous. That's a difference. So method B is normally the method you do discontinuous, method A continuous. But it can be vice versa as well. I will come to that later. So if we look at 6914, that is continuous elongation. That method is in fact called aging. And only method A in that standard is really relaxation. Because there we extend the test piece strip, normally 50%, and measure the decay in the force. Method B in that standard is done in a similar way. We extend the sample, the test strip 50%. We record the force, but then we unload it again, so it's not stretched during the aging time. And at suitable intervals, we extend it again and measure the force at 50% elongation. And that means we get, in fact, to measure the modulus change. It's not the same as the relaxation. But that is also an interesting thing. It's possible to do in the same instruments, by the way. If we talk about what happens in our rubber material when we do relaxation tests, or aging, in fact. If we compress or stretch the material, we have first the physical relaxation. That is only a rearrangement of the polymer chains and fillers, which will find new resting positions or places during the compression. And nothing is really destroyed. It's just the physical. That one we want to get, say, not calculate or count that in. We want to look at the chemical degradation due to aging. And the chemical degradation is mainly then that the molecules get shorter. They are by thermal aging, oxidative aging. And it corresponds quite well if you do tensile tests and look at the elongation at break. The elongation at break during, if you age some rubber material different times, it always goes down, become lower, and that reflects the shorter molecular weight of the short material. But in rubber, we have another thing. We can also have some continued cross-linking. If we have not cured the material properly before we do the test, we will also get some extra crosslinks in the compressed state. And that is affecting the result, of course, but not so much as it will affect the result if we make compression set, because there you see it much more. But it's always, say, a good idea to have a good cured material when you do a test. Otherwise, it will not be what you expect it to be. The relaxation test was developed in England, and it was standardized in ISO during the 80s, in the middle of the 80s, 1980s. And there were really no instruments at that time for doing this test continuously. So I was participating in that standard group, and I worked at that time at the National Testing Laboratory in Sweden, or Testing Institute. And we found that the best thing is to measure continuously and not measure discontinuous, because then you get much more errors. So this was the first design of a continuous test rig. And of course, we also needed a heat source, and we used a cell oven for that purpose. But the cell oven was quite small cells and deep cells, and became quite long. We even started with let's say, computer software. This was in the early 90s. So we recorded on a tape strip recorder. And the longest test we made was 1 year. I will show that later on, which we recorded on a strip recorder on paper, running at the lowest speed, but still it was a lot of paper to look through after 1 year. The instrument at that time was developed by Wallace in England and was measuring in the test fixture. You see one in the picture here, where a load cell was fitted to a pneumatic cylinder, more or less, and compressed the sample inside the test rig a little, so it didn't have any connection with the spacers anymore. According to that method, it's allowed to do a little extra compression to have the sample getting free of the spacers, so it can be, counterforce can be measured. But it is very tricky, and it's quite tricky to get repeatable results. That test rig is then put into an oven to make the aging at an elevated temperature and taken out at suitable intervals. Quite a lot of manual work and quite a lot of errors can be introduced. We at Elastocon, we developed a similar instrument, but we had found that there were some important factors. And one was that compress the sample to exactly the same compression every time. And we made this, we called compression tester, and there we could compress the samples within 1,000 of a millimeter, the same every time. Then we could get more repeatable results. But we have discontinued to make this because there are very little request for it. The method B is also today used quite a lot in measuring in a tensile tester. If you have a modern tensile tester, the elongation measurement is good enough, but in older instruments they are not good enough. You must be able to measure in the range of 1000 millimeter. We'll come to that later on. To the right, you see a test jig for this kind of measurement. Here is a graph from the SAE standard, where this intermittent test is described with a test jig similar to the one we saw before. And the way of determining the force is that you measure the force while you make a further compression. And when the rubber sample don't have any connection or touches the spaces anymore, you get say another curve, and you then take the value as it indicated here. The first steep part of the curve is the metal, it's the deformation you are measuring, and then it's the rubber deformation. And it can be done if you have a tensile test with a good measuring system. The continuous instrument is also a little kind of a tension compression rig, but it's compressed manually because we only need to compress it once when we start the test. We have a load cell and an PT100 sensor connected to an amplifier box to be able to get the values into a computer. The setup could look like this: an oven, a cell oven. In this case, we have a cell oven with 6 different temperatures, so it will be a more flexible type of testing. And an amplifier to the left and a computer to the right. It's possible to test in several ways. Compression is the normal one, you see the first. If you test in tension, we use a strip and clamps. And then to test in liquids, we have containers. There are 2 versions of containers. You can use not airtight. That means that they are not really airtight, and then you cannot test 2 volatile liquids or at 2 high temperatures. And later on, we developed airtight up to 3 bar pressure. And then it's possible to measure oils and fuels and liquids, and also water up to 145 Celsius. That means 3 bar is the maximum pressure limit we have. The normal ovens, they have a steady temperature. This is an oven where we have cycling temperature, and it's equipped with cooling water. You see the flow meter in the front. Here we can cycle between an elevated temperature up to 300 Celsius and down to room temperature 23 Celsius. It means we can do the method B, where the measurements should be done at room temperature, and the aiding at higher temperature, we can do that automatically, and we don't need to take the test jigs in and out of an oven and do manual measurement. A method B curve can look like this. The red is the temperature. Here you have done cycling from 23 Celsius up to 250 Celsius. The green is the force. And every time we go down in temperature, the force will go down due to shrinkage of the rubber. And the interesting thing is, in fact, the value of the peaks, say the downward peaks, so they change with time. And that has been a little job to evaluate originally, but now we have improved our software, so it's more easy to do it. We have a function where we let the software find the 23 Celsius temperatures, and then we can get the plot from the times when we want to measure 23 degrees. So here we have, I think, 24 hours, 72, 96, 168, and so on. Then we can get the plot of the force at room temperature, change in force. Then you can plot the report looking like this. Here we have, say, when you run method B, you always start at room temperature. You get the original F0 value, if it's possible to see here. So the test starts there. When we increase temperature, in this case only to 120 Celsius, the force goes up due to the volume expansion of the rubber. Oops. Sometimes it can go up to even twice the original force if you go very high in temperature. And then we have the first down here. And now we can also plot this curve. That was from the graph before. We got these values. And we have the temperature. In this case, it's shown below. So now we can do also method B automatically and have the computer finding the values and this program the cycling in the oven. Another thing we have developed recently, or no, recently is 3-4 years now. It's in a project we ran together with some car companies, Volvo and Volvo. We have 2 Volvos, as you may know, and Scania and the Research Institute in Sweden, of looking at the relaxation test of biofuels. Biofuels are much more sensitive for aging than the rubber. So we need to change the liquid, change the fuel during the testing. And to do that manually is a little messy job. So we were asked to develop an instrument where we can pump in and pump out the oil. So we have a cell oven and a rig equipped with a lot of hoses and small tubes. And in the cabinet to the left here, we have the pumping and the control of the pumps. And we can have also an agitator in a little container on the test rig to have it uniform. So we first, for biofuel or biodiesel, we had a continuous replacement of the liquid or the fuel. So with micro pumps, we pumped in a little, we pumped out. But we also had a system introducing air via the flow meters to the left here. And to distribute the air inside the container, we need the agitator. Otherwise, you can't have that. And of course, in a fuel which is used in the fuel tank in a car or a truck, you have air present. So you need air during the aging. 2 years later, we made another project with this, the same participants, but this time we looked at motor oil. In motor oil, you also have air present. So also there it's interesting to introduce air in the system. We also made a little holder here so you can put in samples, could be O-rings or small tensile bars. So you can do these, say, other type of test after you finish the relaxation test, but they have been done in the same environment. This can be also, say, adopted on all normal relaxation rigs. But anyway, here is an example of a test we made with a conventional test in a closed container. Normally, when you test rubber in a liquid, you put it in some rubber in a liquid and close the lid. And then the oxygen will disappear quite quick. But in this case, we had applications where we have air present. And then we added the aeration. And you can see we get much more degradation, more relaxation when we have the air introduced. In this case, it's an I think it was an HMBR material tested at 140 Celsius in motor oil. So this has been introduced now in ISO, so we can add that to the aging of rubber in liquids to have an aeration as well. If you look at the accuracy of the system, the idea with continuous system is to avoid touching the sample, moving the samples, handling the samples during the aging, because all that introduces errors. And here is a very early test where we tested the same material in one rig at different test periods, and they correspond quite well. In the end, you see the red curve goes down, and that's because we let it cool down to room temperature, and then the force will go down due to the shrinkage of the rubber. So the rubber shrinks about 10 to 20 times more than steel, or expands, which way you want to go. Another repeatability test, 2 rigs at the same test period. It may happen that they don't show so accurate, but often they are quite similar. What can happen if you have a difference between the curves can be the lubrication of the samples. If that is not done properly and you get some friction, you may get a little difference in the curves. We found that there are some factors which are very important. That is keeping a very constant deformation and keeping a constant temperature. Here is a curve. The standard test piece is 6 to 6.3 millimeters. So if we assume we have a 6 millimeter thick test piece, normally it's compressed to 25%. It means 1.5 millimeter. In this case, we have measured the force from a sample compressed at 1.5 millimeter and further increased the compression to 1.6 millimeter. Then on a 70 hardness material, the force increased. It's about 40 Newton for 1.1 millimeter. That means 4 Newton for 100 millimeter. So we need to be better than 100 millimeter, in the range of a few thousand of millimeter, to get repeatable results. But of course, if you have a softer material, it's not so critical. But many seals, they are more in the range of 70 than in 45. In many measurements, you have errors, but if you know about the errors, then you can compensate for it. The error we have mainly is the stiffness of the load cell, and also say the stiffness of the whole test rig, but especially the load cell. The load cell is being deformed. It's the way a load cell is measuring the force. So it's getting a little shorter when we compress something. And when the rubber then relaxes, the load cell will spring out, because it's in fact a very stiff spring, and compress the rubber a little more, and then we get an error. There are 3 ways of handling this, which we all point out in our manuals. First, you can disregard it because you run comparative measurements. You have the same error in all measurements. Or you can do a manual compensation. That means on the dial gauge on the instrument, you can see how much this has been, and you can do a compensation there after a couple of hours, after 1 day. Or we have also put in the software calculation, which makes the compensation. And there is a compensated curve, that's the red one, and the blue one is uncompensated. So without compensation, you get 2 good results. And with compensation, you get a better, more realistic result. But it's possible to see both of these curves in the software when you do the evaluation, both the compensated and not compensated. Temperature is always important when you talk about aging, but also for other factors. Here we have a test rig standing in the room temperature. The blue curve in the bottom of this graph is the temperature variation in the room. It's a little high, but it's within ±2 degrees, which is the standard temperature in the laboratory. In the blue curve up here, we see the force. It corresponds quite well to the room temperature changes, because that is the difference in expansion between the rubber in the test rig and the rubber in the test rig and the material, steel material in the rig. It gives this. So we need to keep the temperature constant. And in the red curve, we have used the so-called room temperature cabinet, where we keep temperature within plus minus 0.2 degrees. And then we can get a nice force curve, which is not influenced by the room temperature. That's one thing to eliminate variations. Next thing, we have a test rig standing in the cell oven. Then the lower part of the test rig is, and the sample, they are kept at constant temperature. But still, we have the upper part exposed, and the load cell is also sensitive for temperature variation. The green here is the same room variation you saw in the graph before. And the blue curve here is the result in the force. It's still influenced by the room temperature. So if we also manage to control the temperature on the upper part of the rigs, we get the red curve. We can get the stable reading. And this is the setup we used many years ago to show this. We had one oven with the rigs like this exposed. We had one rig standing in the room temperature, it's standing behind that, you can't see it. We have one box here, which is keeping the room temperature for the whole rig. And then the oven with the hood where the temperature is stable during the testing. The important thing is not exactly what the temperature is within this hood, but just that we have a constant temperature, not a varying temperature. You can see by the computer appearance that this is not a recent picture, it's some years old. But I think the results are still valid today. Here I come to the graph we made from that test at the Testing Institute, where we tested for 1 year. We did a lot of tests on sealing rings for water pipes, which is still quite a lot of interest in that area. And we tested 2 rings from 2 different manufacturers at 70 Celsius. And after some 100 hours, we could see that one seems to be much better than the other. And then there were people who wanted to do an extrapolation up to 100 years from these figures. There were a lot of discussions in the ISO committee about that. But we had results for 1 year, and then they look different. The one looking good to begin with, after 1 year, it's not much left of the sealing function. But the dotted line, we still have a sealing function which may work if the pressure of the seal is not too high. You can always speculate what is the difference. I know that the solid black line is an SPR ring. The dotted line, I don't know the polymer. Can be different polymers, can be different antioxidant systems. But it shows that it's always important to test quite long times and not try to extrapolate something, at least not from a 1 temperature test. Now we come into how we estimate the lifetime. This is a picture which is too many characters, but I took the copy of the standard to explain what we are doing when we estimate lifetime. At the chosen test temperature, the variations in the value of a chosen property, and this property we have chosen is the counterforce. You can do this type of evaluation and do the elongation at break, or compression set, another property, which is important for the function of the product you want to use the material. And we determine this value as a function of time. And the testing is continued until we have reached what we consider to be end of life or something like that. That's always the difficult thing, to know what is end of life. When it doesn't function anymore. If you don't know that, 50% reduction is normally used. And then 2 more tests are done at other temperatures. And then we can do a so-called Arrhenius plot. Here we have still the same type of sealing rings, these SBR sealing rings. Tested at 3 temperatures, we found at 50% relaxation, we found 3 time temperature points, T1, T2, T3. And these were then inserted in an Arrhenius plot, which is a graph where we have on the x-axis down here 1 over absolute temperature in Kelvin. But we show Celsius here, we show better graphs later. And the time is shown on the y-axis in logarithmic time. So according to the Arrhenius formula, this should be a straight line. And then we can do extrapolation to a lower temperature. But of course, the further we go from the lowest test temperature, the more uncertainty we have. But we can get 2 kinds of information. We can get the lifetime. We say we want a lifetime at 30 Celsius. That is around that value. Or we can also say we want to have the maximum temperature of use. And there we put in a time of 20,000 hours. That is used by the electrical industry, cable industry, to specify the max temperature of use. That is 2.5 years. And if we use that, we find that this material is not really good, much over 50 Celsius. But if we look then at the car industry, they often only use 1,000 hours. And that is down here. If we use 1,000 hours, then the maximum temperature use is 95 something. So if you see a figure telling you what the max temperature use is, always ask how long, for how long time. It's often not 2.5 years. Here we have a material we tested a long time ago. It's a fluororubber, which is one, I think it's the most expensive rubber we have. We tested quite a long time at 3 temperatures, 160, 180, 200 Celsius. We had the force graph looks like this. The lowest temperature of 160 didn't reach more than 40% relaxation. So then we plotted Arrhenius plots for this. And we plotted both 40% relaxation and 50%. 40%, we had 3 values. We got nice straight line. For 50%, we had only 2. But if the 50% line follow the 40% line, I think we are still can use the data for that. This is plotted in a software we have made in our company, because we found it impossible to make a graph in Excel which shows what we want to show. For example, here we have 1 over absolute temperature in Kelvin. But these figures doesn't tell you very much. So we put in another axis with the Celsius temperatures, and that is not linear and not logarithmic either. But now at least we know where we are. Then we can have a cursor here. We can find out the lifetime at say 70 Celsius. And there's quite a difference in lifetime between these two, 40 or 50% relaxation. We also can calculate the activation energy, and we can see how the coefficient of determination, how good the line is. Normally we get quite good lines. So in this case, we can get a better estimation of a lifetime of the material. So even this fantastic material, at least expensive material, does not last forever. Some other data on here is fluororubber. We have tested 2 different fluororubbers. You see, it's not always you get the 3 points in good line. It happens, and then it must often is that the highest temperature is too high, and then you don't get the straight line. But the interesting thing here is to show the difference between 2 types of fluororubber. So one is better above 150 Celsius, and the other is better below 150 Celsius. So they have quite different activation energy. The same thing with comparing EPDM and thermoplastic elastomers. They show quite different activation energies. And TPE's material are quite often quite better than EPDM, in fact. Depends, of course, of the type of EPDM, the curing system and other things. We've done quite a lot lately in the last 3-4 years. We tested quite a lot of relaxation on sealing rings for water pipes. Sealing rings for water pipes or wastewater, not hot water. We have a lot of, say, pipes in the ground in all cities, and they start to leak, or have done quite a long time sometimes, because originally we had natural rubber seals and they don't last so long, and then we changed to SBR seals, and now we have EPDM seals. But there can be quite enormous spread in EPDM. So this is a project we made together with Trelleborg. I can mention their name because they have published some of these results. And that is samples taken from all kinds of manufacturers. I don't know more than the polymer type. And we can see we get quite a spread in lifetime estimations from 56 years to 5,600 years at 30 Celsius. I also added a peroxide cube. That was not a sealing ring compound. It was a compound for some other use, but it was an EPDM. And there we see that the peroxide is quite much better at high temperature, but not so, well, it's still the best, but it's not so much better at the lower temperatures. This is just a few of all the tests we've done on these kind of materials. We have much more. We also tested SBR, also from the present production, and we saw on sales in the market. There we see quite a big difference from about 3.8 years up to 140 years. But please note that we have gone down to 50% relaxation. We believe that the sealing ring in a water pipe with quite low pressure difference will function to much higher relaxation figures. But this gives a good, say, comparison between the materials. We can still make a quite good SBR material, which is, in fact, I think, as good. This was 30 Celsius. A good SBR can be almost in the same range as a poor EPDM. Then we have another type of testing with relaxation. That is part 2 of the standard, where we have introduced temperature cycling. In the ISO standard, we have method A. We do it once a week, go down to sub-zero temperatures to see if you still have some sealing force. We can do method B, where you do more continuous cycling, then you get a little more dynamic effect as well. This was requested by the automotive industry, and General Motors have been the leading company there. They had for some years now a test cycle, which I will show later on, which is quite difficult to meet. Volvo trucks have the similar cycle, but a much shorter one. And it seems as more people are interested in this sub-zero testing, because there we also get a lot of the effect is the shrinkage of the rubber. But the method A is like this. You go down once a week to see if you have some force left or not. That is the temperature cycle. Or you cycle as soon as fast as you can. And every time you go up in temperature, the rubber will be more compressed. And every time you go down in temperature, it will be released. It will be a slow dynamic cycling as well. Here is the General Motors cycling test. it's a little complicated. I don't know the reason for all these, but they have two high temperatures, 150 and 140, or is it 135? And they have two low temperature, -18 and -40. So this is the temperature, the red, the blue is the curve. The cycle starts at room temperature, and then we are at the F over F0, 1. So we take a reading at room temperature here. Then we immediately go down to -40. Then we can see the effect of just the shrinkage. We have no aging done yet, just the shrinkage. Then we have a warm cycle, and then we go down again to -40 here. Here is -18. So compare that one with that one. So after some aging, it decreases quite a lot when we have shrinkage plus aging. And then the -40 values go further and further down here until they are at 0. So this material didn't pass the test. The 3 last cycles are down to 0 counterforce at -40. We still have some counterforce at -18. So this is a quite tough test. To do this test, we have an aging oven with 6 cells, not with the same temperature. And the temperature is controlled by a liquid thermostat to the left here, connected to the oven. Also here we keep temperature constant up here, but we have more forceful peltier elements system there, so we can both heat and cool, because we want to keep the temperature constant. So we need to heat when we go down in temperature, we need to cool when we go up in temperature. Another instrument we developed now quite a lot of years ago now is an even more automatic relaxation and creep tester. It can also test creep, because here we have 3 test rigs. They are motorized for going up and down, and we have a servo motor doing the compression of the sample. And then we can have a temperature up to 300 Celsius inside here. There's little data. The important thing here is if we want to measure creep especially, which we can do because we can set it on a force level and keep that force level and measure the creep. We have an accuracy of 1,000 millimeter and a resolution of 1/10,000. We can see that on this graph. Here we are doing a relaxation test. The red is the temperature, 70 Celsius. The blue is the position. Why does the position look like this? Yeah, because we have quite a quick reduction in force to start with. And in this case, the servo motor will compensate for every 1,000 millimeter. It will compensate 1,000 millimeters. So all the steps here are 1,000. If you look out here there is 1,000 between these 2 steps. So we can measure with 1/10,000. And the correction gets less and less when we continue the test. So with this kind of system, we have a correction for this stiffness in the load cell, which is automatic. And if we look at the graph for creep, we still test at 70 Celsius. We apply a load here of 900 newtons. And the blue is the change in position. That means the creep. And the steps here, I think, is still 1,000 millimeter steps. So it's a combined instrument, and it can measure creep for both plastic and rubber. Yeah, before I leave this, I will mention one more thing we have made, that in our relaxation rigs, we have done a creep fixture we can fit in a relaxation rig. So we have in fact been running relaxation tests on plastics, but in bending mode, in flexural mode, in the creep fixture. And that seemed to work for quite hard plastics to do the test in a normal relaxation rig. And that is then the kind of measuring creep, but measuring the force instead of the elongation. So we believe that stress relaxation tests are very effective for conducting aging tests, as we get quite a lot of information with little effort. And with effort, I mean man hours, and especially if we use a continuous measuring system. Thank you. Now it's open for questions, and if you want to have to answer or discuss something, you can write it in the chat window, or you can raise your hand and we can discuss that. I will just start to